The knapsack problem. This video is about, guess what, the knapsack problem. What is a knapsack? Let's see. Knapsack image. If you digit knapsack, you get immediately knapsack. This is an image specifically of the knapsack problem. Okay, this is a knapsack. Okay. You have to go to hike in the mountain. You have a small knapsack with you with a limited capacity, let's say 10 liters. Okay, we use capacity and not weight because otherwise weight will create problem. The biggest problem of knapsack is usually capacity. Okay, you have some object to put inside, usually tons and tons of objects. Okay, but they exceed obviously the capacity of your knapsack, as always happens. You can imagine the same problem as suitcase if you go on a journey. Imagine, for example, you have 4 objects, okay? Let's say water, blanket, food, binocular, okay? Each one has sides, let's say 3, the bottle of water, the blanket, okay? The food, the binocular, 3, okay? Each one has a utility. The utility of water, usually it's slightly larger than the utility of a binocular. Well, it depends on what you have to do. Utility 5, 7, the blanket is the most useful at the end. 8, the food, you're gonna starve. Binocular 4, okay? Obviously you would like to maximize your utility, but you have a constraint on the size. The size cannot exceed the size, the capacity of your knapsack. Okay, clearly you are old enough, you are grown enough that it's not necessary to tell you that this problem, it's not because to help you planning your trips, but because it's a simplification for several other categories of problems. For example, here I spent 5 minutes thinking and I got some example. Images on a web page, you have to build a web page, you have to put some images. Well, in theory the web page is unlimited, but I mean, you can't, the user after the second screen will get upset. So you have to decide which image to put. Each one has a size. Okay, some are more useful than others. Information delivered to customers. Also here, whenever I buy a new product, whatever it is, I read the first half page of the instructions, then I give up. Okay. Well, so you must try in that half page to put the most useful information, which usually it's not the case for products, in which in the first 4 pages there are 7 instructions which are totally useless, such as don't put your fingers into the electrical socket. Okay. You also, for the timing of your work activities, you can imagine your work activities have a size, okay, in time. You have a maximum time. Okay, who is writing to me in WhatsApp? Oh, a lot of messages. Okay. And obviously you have a limited time. Resource allocation, any resource allocation problem can be mimicked with this thing. And also, it may seem strange to you, navigation systems, they don't use exactly the knapsack problem, but they will use the same algorithm that I show below. You can imagine the pieces of road as the item. You can imagine you want to minimize the time, so not maximize, but minimize the time. Each piece of road that you add, it's extra time. And you don't have a limit on the size, but you have a constraint, which is you must reach your goal. Okay, or at least go after your goal, but at least reach your goal. There are tons of other situations. Let's start immediately. So first of all, if you have not yet focused the problem, so you have a maximum capacity, each item, let's call them item and not objects. Items. Because object makes confusion with the computer object of the items. Okay, you have some items, each one has a size and a utility. Okay, and you have a knapsack in which to put the item, which has a limited capacity, so maximum size of the objects. Okay, you must maximize your utility. I will tell you there is a variant of this, an interesting variant of this problem, which takes into consideration the fact that some items combined with other increase or decrease their utility. Imagine if you put here, you have water, blanket, food, binocular. If I put also tea, well, if I have the tea alone, it has a high utility. If I have the water alone, it has a high utility. But water and tea together, the utility, it's not zero, but drops, because one is a replacement for the other. Okay. Or you can have some items which act vice versa. If they are together, they raise their utility. For example, if you have the charger by itself, the charger of your telephone, by itself it has a utility of 0. But if you have also the telephone, the utility then increases. Okay, so there is a variant of this problem. We don't deal with this variant because it's non-linear and the algorithm for solving it is really difficult. The very first thing we talk about are the data structures. Not the data structure that we use in the algorithm, but at least the data structure in which we will put the basic data that you have, so the one described here. So, we have, what do we get in input? In input we get the objects, their size, their utility, and the maximum capacity. Clearly the maximum capacity stay in a variable, it's a number, that's it. Objects, obviously, is a list. Here you have the list, for example. Okay. The size is a list. And the utility is a list. It's very important that in case you change one of these three lists, also the other one must be changed automatically. So for example, if you decide to sort your items by utility, and we will do it, so starting from the most useful one, going down to the less useful one, you must sort the other two lists in the same way. Otherwise, you will get the list of utilities which does not correspond anymore with the list of size and the names of the object. So beware that these three lists go together. We could put them into the same list, but then it will become a list of lists and your brain will start to burn. So for the moment, you will have biggest problem later on, but for the moment, let's keep the thing simple. So three lists, beware that they must be kept synchronized. What is the output? The output, well, for each item, I want to know whether I have to put it into the knapsack or not. So the output will be a list of true, false, true if I put it into the knapsack, and false if I don't put it. Let's call it status. For example, true, false, I take the water and the food. So I'm planning on to fill up my stomach, and who cares about the rest? Who cares about the cold, and who cares about the view? Okay, so this is the status. The status will be the output and will also be a variable that we'll use during the process to find out the solution. Okay, how can we solve this algorithm? Well, first of all, how would a human person solve it? How do you have to solve it every time you prepare a luggage? Okay. Well, people solve it usually in this way. Well, there are two approaches I see. The one is to throw everything inside the knapsack or the luggage or the suitcase, even exceeding the capacity, and then removing the less useful items, or removing the biggest items. You can see there is a trade-off, because maybe a big item is very useful. Well, if you have a big item which is not useful, you remove it. But if there is a big item which is also useful, it's hard to remove it. Or a small item which is not so useful, but it's small. So there is this trade-off in this problem. So this is the first approach that I see. So exceed the capacity and then go down. Okay. Second approach that I see, start from the item which is absolutely you must have, the most used. This is what I take. So first I fill my suitcase with all the technological things, which are the items which must be there, and then I put the panties and my clothes and etc. And then at last thing I put the toothbrush, which can be bought also in the place where I am. Okay, so put inside the items which are most useful, and then go down in utility order. Okay, well. A computer can, you have now learned that most of this kind of problem can be solved by brute force. What does it mean brute force? You try all the possible combinations. Well, for 4 items, how many combinations do you have? Well, you have the combination nothing, empty. I see people in the mountain hiking with no knapsack at all. And I'm wondering if they're thirsty, if they cut themselves a finger, if they break a shoe. I am inside full of things. Okay, you can take nothing. That's this one. Okay, only the water, only the blanket, only the food, only the binocular. The water with a blanket, the water with the food, the water with a binocular. the blanket with the food, the blanket with the binocular, and we are at 10. The food with the binocular, 11. Water, blanket, food. Water, food, binocular. Wait, the water, blanket, food. Water, food, binocular. Water, blanket, binocular. And we are at 14. And then blanket, food, binocular, 15. And everything, 16. You have 16 possibilities here. Well, now, perhaps after several exercises of this type, you have learned that usually brute force approaches have possible combination for one item to the power of how many items do you have. So here, the brute force approach requires 2 to the power of n attempts. In fact, I've calculated 16 in this case. So 2 to the power of 4, 2 by 2, 4 by 2, 8 by 2, 16. So 16 attempts, where n is the number of items. I will have to make an automatic replace. Okay. Each attempt requires you to calculate the size to check that it's possible to put all the stuff into the backpack, and the utility, because you have to find one with the maximum utility. So size and utility. So to calculate the size, you need to multiply each size by true or false. Well, okay, in theory you could go through, if it is true, take the size and sum, if it is false, don't take the size, but it's equivalent to multiplying. So you need a multiplication of an integer with a boolean. It's not that bad, it's better than multiplying two integer, but however, let's say, this kind of multiplication, you need n multiplications, and also for utility, so 2n multiplication per attempt, so 2n multiplication per attempt, 2 to the power of n attempts. Well, this part here doesn't modify too much the calculation. It's this part here which is terrible, however. Okay. Because if you have 4 items, you have 16 possibilities. Most of them are silly. For example, take nothing, or take all of them which exceeds the capacity. However, many of them are valid. Okay. Look how the number grows. I tried for n equal 10, and this number is 20,000. 20,000, so for 10 items. N equal 20, it's 42 millions. So 42 million possible combination. N equal 30, 64 billion combination. So how many things do you put in your, not in your suitcase, but just in your backpack, the one which you come at university? I'm pretty sure that you have inside 20 items, big and small. Take it, open it and check, at least 20 items. So if you want to solve if you suppose that other 10 items you have left out, if you want to solve the problem of each item to carry at university, let's fix myself, okay. You have to examine 64 billion case. So the next time that you forget something at home, well, it's not your fault. It's because the combination were too many and you didn't observe that combination, which could have been more useful than the one you carry in. Or the next time that somebody complains, you haven't taken with you this thing, and say, well, there are 64 billion of combination, don't break my... Okay, so this is the complexity in the worst case. But in this kind of problem, in which you have to maximize, there is no worse or good case, because you must examine all the possibilities, because you never know, maybe you have found a very good combination, but there is another hidden combination that you haven't examined, so you must examine all the combination. So if you use brute force here, it's not like finding, for example, the password, cracking a password, in which when you found it, found. Here, once you found a valid solution, you must look at all the other, because you have to maximize the utility, so you must be sure that it's a maximum. So, to have better also the timetable. The timetable, you stop once you find a solution. But now here you want to find the best solution. Can't we do something better? Yes, don't worry. As I told you, usually human persons, whenever they have to fill the suitcase, some of them start with the most useful items. Okay. So before introducing the algorithm, which makes this work slightly easier, not so much easier. Okay, let's find out first how to sort the items. I want you to develop here an algorithm which sorts the utilities. You say, we have already done. Yes, you have already done. But you had done an algorithm which sort the utility, and that's it. Now I want an algorithm which sort the utility, and any operation that you do on vector u, on list u, you must do the same operation on list s and on list n. Because if you put this third item, which is the food, at the beginning, also its size must go at the beginning, and also the name food must go at the beginning. Okay. And this also to answer one of your colleagues asked me during the lesson, why do we have to develop sorting algorithm if there is that nice list.sort method? Well, that's one possible answer. You have to develop because sometimes the list.sort cannot be used. If you use here u.sort, it will sort u, but s and n will remain the same. And no, you cannot sort s and sort n because the sorting of s and n is different from the sorting of u. So now I choose bubble sort. You can choose any other algorithm that you want. So paste the code here of your favorite sorting algorithm. Pay attention to the one sorted from the biggest one, to the, it's strange because it's reversed, to the smallest one. Okay, so from the biggest one to the smallest, it's reversed, so the biggest one to the smallest one. Okay, usually we sorted vice versa, from the smallest to the biggest. So take their favorite sorting algorithm, reverse it. Usually it means reversing a smaller with a bigger or something like that. Okay, and any modification that you do to list u must be done also to list s and to list n. This must be done during the algorithm. You can't do it at the end. You won't be able to do it. Okay, you can see I have written my code here, then I deleted it so I can leave the exercise to you, and this will be my result. So you can see I sorted the utility. No, the result is wrong because I deleted my code, sorry. So the result is wrong because I deleted the code and then I ran it again. So the result is the same as the input. So, but the result should be 8, 7, 4, 5, 4, 4, 6, 3, 3, food, blanket, water binocular. That's the result. Okay, here it is. I've written it. Okay. Once you have developed this thing, we will need it later. Let's talk about the algorithm which usually solves this problem. It's not an algorithm which improves the complexity, because at the end, if you are unlucky, the complexity is still 2 to the power of n by 2n. But at least in the average case, you will do much less operation. What is the observation? The observation is the following. Where are the items? Here. There are some situations which you don't need to analyze. For example, do you really need to analyze the situation in which you take all of them? Well, no, because it exceeds the size. Imagine if you have inside an object whose size is larger than the capacity of the knapsack. Well, there is no way for you to put it inside, so no reason to examine it. But also there are other situations. Imagine, do you really have to examine situations in which you take only one item and not the others? Well, your utility will be very low. For sure there are better situations. So there are a lot of situations which you actually don't need to examine. So all the possibility branches, you will see we will develop a tree here with all the possibilities. Several branches will have suboptimal solutions which don't even need to be taken into consideration. Either suboptimal or solutions which already exceed the capacity. For example, if you take blanket and food, you have already 10 of size. It's pointless to examine what happens taking blanket, food and something else, because you exceed the capacity, full stop. Okay, so several situations it's silly to go on examining. So we must find a way to cut. It's technically called prune. If you walk in the garden, you know the meaning of pruning. You prune the branches. So cut some branches which lead to things which are suboptimal, or things which, why the luminous light of my video change? Okay, suboptimal, or here suboptimal, or which are totally impossible. And the algorithm we use is called branch and bound. Okay. It's a heuristic technique for maximization problem. It doesn't improve, as I told you, the worst case complexity, but only the average case. So on average you will do much less operation, but if you are unlucky you still have to examine all the cases. Okay. The strategy is take the problem and branch it into two sub-problems. Okay. Each one we will examine whether it's promising or not. So whether it promises us to have a high utility or whether we are pretty sure that the utility of that branch will be low. Okay. We will examine only the branch which the largest promising utility, so the one which promises us to have a large utility. So this is called branch, and then put a bound on the utility. But let's see the example in practice. Okay. We start always with a previous example, so you have 4 items. Okay, 4 items, here are the items. First of all, we start with a situation in which we have nothing into the knapsack. So knapsack is there empty. Okay, so if you have nothing, the current size is 0, the current utility is 0. What is the maximum potential utility? Well, we haven't taken any decision, so we haven't thrown away any object, or neither throw in. So the maximum potential utility is all the utilities. So 8 plus 7 plus 4 plus 5 plus 4, 24. Okay? So this is the start of our tree. It's called root. This yellow rectangle is called root. Because this is even if you don't believe, this is a tree. This is the root. Okay, maximum utility 24. It's a potential utility. It means that currently we haven't taken any decision on which item to put and which item not to put, but we are sure that even in the best case, so all the items in, the maximum utility we have is 24. Current utility 0, we haven't taken anything. Weight 0. Sorry, I talk about weight, but it's size. Okay, well, it doesn't matter. Okay, now we branch. So branch and bound, or we have to branch. We take the first object. Since we sorted the object in utility order, the first object is the most useful one. So you take the first object, which is in this case your food, and we say, do I put the sandwich inside or not? The sandwich 3 apples and 4 bananas inside or not? Okay, they are pretty heavy. Okay. So you have 2 branches here. You put your bananas inside. I call it A1. It means that item A, the first one, is taken. And here I call A0. Item A is not taken. So we leave the banana home. In this branch, we are sure to take the bananas, the sandwiches. In this branch, we are sure not to take the food in. Okay. Let's examine the utility. Well, you take the banana, so utility is the utility of the banana. It's the only item that you have decided to take. The weight. Okay. Here, utility and weight stay at 0 because the only decision you have taken so far is leave the banana home. Okay. Maximum utility. Your maximum utility is still 24. You have decided to take the banana and you potentially can take all the other items. Here, the maximum utility has decreased because you have decided to leave the bananas home. So now you don't have a maximum utility of 24. Your maximum utility is 0 bananas and all the other items you could take. Okay. Now you have 2 branches. This branch here and this branch here. What is the bound part of the algorithm? The bound part of the algorithm is this max utility because you are sure that everything which belongs to this branch will never exceed 16 as utility. So this is the bound. So everything that belongs to this branch will never exceed 16. So which branch do you choose to analyze further? Well, it's this branch and bound and choose. So you choose this one. Okay. We take the one with the maximum potential utility. Okay, let's see this one. So we have decided the first. So in this case, we are sure bananas inside. Second item, in order of utility, blanket. So we put the blanket inside, we leave the blanket home. So banana and blanket, banana and no blanket. Okay. Again, if you put the blanket inside, your utility increases by the utility of the blanket. So utility is calculated true banana by utility of the banana, true blanket by utility of the blanket. The rest you don't know. Weight, same thing. Size of the banana by the utility of the bananas. By the size of the bananas by true. Size of the blanket by true. Here, your utility is calculated as utility of the banana by multiplied by true, utility of the blanket multiplied by false, which is 0. In computer science, false is 0, so the utility is only the utility of the bananas. And the sides, it's the same thing. Sides and utility are calculated exactly in the same way in this algorithm. The maximum utility, here is still 24 because you have decided to take the second item. Here you have decided to leave the second item out, the blanket. So utility drops because in this branch you will never include the blanket anymore. So maximum utility is 17. Now you have 3 branches open. Don't forget this one. This one is still open. 3 branches open. You have this one, and this one. So 3 branches open. Of these 3 branches, you will consider the one with the largest potential utility, so the one which opens more possibilities for you. Okay. This algorithm, by the way, it's also an algorithm that can be used in a variety of situations, even in business decisions. You take the decision which gives you more possibilities. Then you see what happens, and you choose, oh, this one is impossible, so it's an algorithm which can be used also in business decisions. Okay, let's see here. So food, blanket, you have to take a decision over there. What is the next one? Water. So food, blanket and water, or food, blanket and no water. Food, blanket and water has a little problem, unfortunately. If you calculate the utility, oops, here there is a bug, there is a mistake. Here utility is not 15, it's more, because the water, I will have to fix it. Okay, utility is not 15, it's slightly more. However, the problem is that the weight is already 10 with the food and the blanket. If you take also the water, it will go to 13. Your maximum capacity is 10. So, I'm sorry, this one is eliminated. It exceeds your maximum. It's eliminated together with all its sub-branches. Because now it's pointless to decide whether taking the binocular or not. Because already with food, blanket and water, you have exceeded the capacity of your knapsack. So it's deleted. The only branch which survives after this branching, it's food, blanket, and no water. So you take the water and you empty it in the sink. Okay, here the utility stays the same because we have decided that no water. The size stays the same because it's exactly like this. You have decided not to take the water. However, your potential utility decreases because at this point you have decided that you will have no water. Okay. At this point you have open. This one is not even open, it's deleted. You have open this one, and this one. This, and this. Let's see, maximum utility 19, maximum utility 17, maximum utility 16. We will go on with this one. So current situation is a food, blanket, and no water. Okay. Let's see, split, food, blanket, no water, but binocular. Again, the utility increases, but the size also increases beyond the limit. So this is impossible, not even consider. Food, blanket, no water, no binocular. Size 10, utility 15, maximum potential utility 15, because at this point we have reached the alt element. Technically, this thing is called a leaf. This is a tree, this is the root, these are the branches, and this is a leaf, because you don't go any more farther, it's a leaf. You have taken a decision for all the items. So we have reached a leaf. So we have now a leaf with utility 15 and maximum utility 15. It's a leaf, so you don't have any open situation anymore. Okay. We have here an open branch with maximum utility 17 and another open branch with maximum utility 16. So do we take the leaf? We have found a solution now. Do we take this as a solution? No, you cannot. because even this is a solution with a good utility, you still have this branch open with a potential utility larger, and you still have this branch open with a potential utility larger. So even though this one is a solution, you are not sure that it is the optimal one, because this one or this one may lead to a better solution because the potential, the bound is higher. So you keep this leaf as a potential, as a solution, but you go on examining as usual the one with the largest potential utility, this one. You branch. So in this case, I remind you, we take the food, but we leave the blanket home. The blanket, unfortunately, is very heavy. Okay, it's an old style blanket, the one made of wool, very thick, more heavy, it's large. Okay, you decide food, no blanket, water, or food, no blanket, and no water. Well, food, no blanket, water, potential utility remains the same, the utility increases, and the weight also increases, you have added the water. Food, no blanket, no water, utility and size stay the same, and the potential utility decreases because you have decided to leave away forever the water. Now, open branches. You have a leaf here, this one, with utility 15, an open branch with utility 17, an open branch with utility 12, and an open branch with utility 16. You take this one. We branch it. So we have food, no blanket, water, and we have food, no blanket, water, binocular, and food, no blanket, water, and no binocular. These are leaves, so our terminal. We have taken all the decisions. We can't branch anymore. The utility here increases from 13 to 17 because we have added the binocular. Also the weight, however, increases. Luckily, it's still 9, so it's still below the maximum capacity. Here, utility remains the same, the weight remains the same, because we have just decided to throw the binocular out from the window. Okay. And now the situation is, we have this leaf with utility 15, this leaf with utility 17, this leaf with utility 13, this open branch with maximum potential utility 12, and this open branch with maximum potential utility 16. Here the utility and the maximum potential utility correspond because it's a leaf, so you can't take any decision anymore, so your maximum potential utility is your utility. So we have 15, 17, 13, 12 and 16. Which one do we take? Well, I imagine that if you had done this examination without writing all the numbers, probably at this point you would examine the situation. But if you write all the number, in particular the maximum utility, it's clear that this 16, and here you have 17, this leaf, you are sure that it will be always larger than whatever you find here. So all this branch will lead to solution in which you never exceed 16 as a utility. But here you have a solution whose utility is 17. So we take it. It's a leaf, we cannot branch anymore, so it's our maximum solution. So this is the best optimal solution. So leave home the blanket, which seemed more interesting, very interesting, but it was not. And take all the rest. Utility 17, size 9. Okay, so you can see that the big advantage of using this algorithm is that you didn't have to examine half of the tree. You can see here, there is a half of the tree. So half of the possibilities were discarded immediately. Also, a lot of possibilities were discarded here and here by the fact that this was already impossible, and this, with a maximum utility 12, it's much better the 17 that we found. So it helped, in particular this one helped us a lot, because we discarded 15, half of the possibilities, which in this case are 8, because we have, this tree has 16 final solutions, so 16 leaves. Okay, this, not examining this one already saved us from examining 8 leaves. Okay, 8 leaves. Okay. Other 2 leaves were saved by not examining this one, and other 2 leaves were saved by not examining this one. So 2, 4, and 8. So we saved 12 leaves examination, and we examine only 4 leaves. So you can see at the end we examine all. Okay, we have to examine also the intermediate cases, but usually if you have several items, this tree goes down very fast. It's the number of leaves which can be terrible. So it saves you to examine a lot of leaves and can save you time. But just for curiosity, let's see. I have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I have to do 13 I have to examine 13 cases, while examining all the possibilities will be 16. We didn't save that much, but because the number of items was 4, if it were 4,000, it would have saved much more. Okay, now this is how the algorithm works. I invite you to rewatch the video if you have any doubt. Okay. You can try to apply it in another example or in your life. So what do I do today? If I do this one, but I can do this one or not do this one. If I do this one, I get this benefit. If I don't do, I still have some potential benefit because I will be able to do other things. Then branch over. Okay. Doing it manually takes a lot of time, as you can see, but I have tried it with a single click, tack, in an instant I got the answer, which is this one. Okay. So, do we need any other data structure? Well, we have a data structure in which we will store, where are they? Here. Which will store the name of the items, the size, the utility. Okay, we have a data structure which is like this, in which we store whether the item is chosen or not. We can make it also partial. So you can also set the data structure. I am on the Mac, so it's very difficult to use it. Okay. You can make it also like this, true, false. In this case, I indicate that I have taken a decision on the first and the second one, but I have not taken any decision on the other items. So the status can be also partial, doesn't need to have all the n elements. If you have less than n elements, it means that you didn't take any decision on the other items. So these are the data structure we need. We unfortunately need another data structure. It's a place in which we will store all the open branches. So you probably have noticed that while going through this algorithm, every time I said, which open branches do we have? For example, here we have this one open, this one open, and this one open. So we must keep track of the open. We don't care about the closed branches, as this one, so discarded, or the closed, this one, for example. So we don't take care of the branches which have already branched, and we don't take care of the branches which have been already eliminated, but we must keep track of all the branches which are currently open, this one, this one, this one, or all the leaves. So everything which is terminal, so which is, for example, in the final situation, we have to take care of this one, this one, this one, this one, and this one. So 5 things. So we need a data structure to put inside these things here. Guess which data structure do we have? It will be a list, because the data structure must also be kept in order. So we build a data structure called BB. We call it BB. Oops. BB. Okay, means branch and bound. In this data structure we'll have element. Each element will be a branch. So which information do we need for the branch? For the branch we need information on the maximum utility, on the size, and this information here. So this branch corresponds to true, true, false. This branch corresponds to false. This branch corresponds to true, false, false. This leaf corresponds to true, false, true, true. Okay, so the items will be like this. into a BB structure. Let's zoom. So 12 is the maximum potential utility, 8 the current utility, 4 the current sides, and true, false, false means that in this branch we have taken the decision to take the first item, drop the second, drop the third, and no other decision has been taken on the other items. So the data structure BB will contain things like that. I'm sorry that a data structure which is a list contains other lists which contain other lists. I can't do it any better. I could do better, but not with the things that we have, not with the tools that we have. So just to give you an example here, at first we have only this one, which is maximum utility 24, current utility 0, size 0, so 24, 0, 0, and decision taken, no one. So decision taken, as you can see, no one. It's an empty list here. Okay. Then you branch. You drop this one because once it's branched, it's not more in our list. So it's not an open branch anymore. You branch, and you have this one, which is maximum utility 24, utility 8, and size 4 here. Maximum utility 24, utility 8, and size 4, and the current decision is first element taken, so true. And this one, maximum utility 16, 0, 0, first element not taken. So maximum utility 16, 0, 0, first element not taken. So this is how the data structure is made, our BB data structure. It's important that this BB data structure be kept always in maximum potential utility order. In this way, in the first place, we'll always have the most promising branch open. We don't actually care where are these branches in the tree, so it doesn't give you any information on the geometry. So if you have, for example, this one, which starts to be pretty complex, you don't have any idea where they are in this schema here. But the important thing is that they contain all the information on the branches. The maximum potential utility, the current real utility, the current size, and which decision have been taken so far. Take, leave, take. Okay. Just to give you an idea, this is the final situation. The final situation is this one. 1, 2, 3, 4, 5, which correspond to 1, 2, 3, because they are in order of maximum utility, 4, 5. Okay. I suggest you to invest some time to check that they really correspond. Maybe I've done mistakes. Almost impossible, but maybe I've done mistakes. Now, not to check whether it's correct what I write, but just to understand. Okay. Because this data structure will be used a lot. This is our representation of the tree. Not really the complete tree, because we are not interested in the old branches, but the current open branches. So currently you see we have 5 open branches. This one is a leaf, and you know that it's a leaf because it uses 4 decisions already taken. This one is a very open branch because you took only 1 decision. It's this one. It's this one. Okay. This one is another leaf. Can you see? Because true, true, false, false. This one is another leaf. True, true, false, false. This one is not a leaf because true, false, false. Okay. Now the issue is, when does the algorithm finishes? Well, as I think about it, you can stop. I have already said it, but stop. Okay. You have for sure arrived to the solution, haven't you? Do I have to tell stop again? So the algorithm finishes, well, when the first thing here, which is the most promising thing, it's a leaf. It means that it has exactly 4, in this case 4 elements. So it has exactly the number of elements which correspond to the number of items you have. So when this one is a leaf, since it's in order of potential maximum utility, you are sure that there is no better branch. Okay? And now the algorithm, which unfortunately you have to develop yourself. Okay? I have put here some comments. I have decided to give you first of all, I have built a procedure already for you. Then I've decided to give you a little schema so you don't get lost completely. Okay, here, copy here your sorting procedure that I've written above. Above. Okay, just to be sure you copy it. Then calc util, given u and the current status, calculate the utility. Okay, so multiply u0 by status 0, u1 by status. Status is true, true, false, false, true, true. Okay, pay attention that status probably has less items than u, because status is only the decision taken so far, so perhaps you didn't take all the decision. Okay, max util, this is different, similar but different. It calculates the maximum potential utility, so it starts as this one for the things that you have already decided, and then you have to add the potential utility of the things that you haven't decided. I don't want to give you too many hints, because otherwise I will offend your intelligence. Calculate size. Well, according to my opinion, you don't need this procedure, but I'm sure that you will feel safer if you write it. However, after having written it, you will realize that you didn't need it. It seems strange, but it happened to me. I wrote it and I say, but this one is identical to another one. Okay. Insert BB. This is a procedure which inserts an element into the BB structure. So maximum utility, utility, size, and the status, so the list of true, true, false, false, it gets inside the BB. You cannot simply append it and who cares, because BB must be kept in order of maximum utility. So you must decide where to insert it. Okay, it's easy to do it, but just to be sure, I've written it completely myself, so you can rely on it. If you give maximum utility, utility, size, and status, it will insert this thing into the appropriate place, keeping BB in order of maximum utility. So you can read my code. It doesn't simply append it, because sometimes you don't have to insert it at the end, you have to insert at the beginning. So it checks where to insert and inserts it appropriately. So it keeps BB sorted. Okay, finally the program. Here the starting situation. Okay. I've decided not to ask you to write a procedure, you write directly a program. In case you want to change the example, you just change this for data here. You don't need to change the rest of the program, just change this for data here. You could write a procedure, but let's write a program, it's easier. Here you have to do it, sort the data by utility, set up the first branch, the root, please do it. If you have doubts about how the root is, look at the picture. The root, utility 0, weight 0, maximum utility. You have to get, don't write 24, I will kill you if you write 24. You have to calculate it. And the starting situation is status, nothing. You haven't taken any decision. Okay. Put the first branch into BB. Well, easy, you have an insert function to do it. And finally loop, take the first element of BB, take it out from BB, check whether it's a leaf or not. If it is a leaf, it means that you have finished. So write the solution in a human readable format. Okay. If it is not a leaf, you have to branch it. Branch means writing two parts of the code, the branch left and the branch right. They are slightly different because the branch left, as you can see from the picture, the branch left sometimes can exceed the sides, while the branch right for sure never exceeds the sides because you simply drop an item. So they are slightly different, the branch left and the branch right. You have both to insert into BB and then go on. And this is my solution. I ran the code when I wrote before deleting it. I ran the code and this is what I write. You can check it's exactly what I do before. Insert this one and getting this one. At the end the solution is true, false, true, true. Take food, leave blanket, take water, take binocular. You have to write the code. Another little exercise for you. Do another example with 10 items this time. However, please, I don't want to see trivial solution. A trivial solution it's a solution, for example, in which you take all the items or you take none of them. Okay. Another trivial solution is a solution in which you take all the items with the largest utilities and you leave the others home. Well, we don't need an algorithm for that. A human can do it better. Okay. So please set up an example. Try to make the ratio utility over size a little not equal for all the items. So if you decide that big items have a large utility and small items small utility, you will have a trivial solution. So run it, get a solution, check that it's not trivial. Okay, if you wonder what is trivial, look on Wikipedia. Is that trivial on Wikipedia? Trivial solution Wikipedia. It's in Italian there is banale. There is also triviality in mathematics. In mathematics, the adjective trivial is frequently used for objects that have a very simple structure. Okay. Trivial and non-trivial solution. Okay. So empty is trivial solution. All is a trivial solution. Okay. So I want something a little interesting. Doesn't have to be whatever. Okay, goodbye. Let's see whether I can stop it.